So once upon a time, most installations were pretty simple. The supply came from the distribution business, through the switchboards, to the final subcircuits and ultimately to the loads. I get that generators have been around for a long time, but they were usually just a changeover switch to the rest of the installation. But now what we're seeing with solar and batteries, a single installation may have a number of different supply types connected to it. So there are three supply types that are defined in the current version of AS/NZS 3000, which are on the screen now. They are normal, alternative, and supplementary. Now, alternative and normal have been in 3000 for nearly 20 years. So the normal supply is the one that the installation is supplied from normally. Typically, this is the grid, and that's the main way that AS/NZS 3000 is written. But it is getting increasingly common that the normal supply is coming from alternative supplies, such as batteries. AS/NZS 3000 typically has a normal supply of the grid, which is the vast majority of installations. But as you can see, the normal supply could also come from a generator or a standalone power system. A new term was added to the 2018 version of AS/NZS 3000, and that is supplementary supply. Typically, this is how a solar inverter works. It needs a normal supply being available, and then it provides a supplementary supply to the installation. Now, the normal supply provides the voltage and frequency reference for the supplementary supply to parallel to. Then the installation will use the energy from the supplementary supply first, and that's how it's got its name. It supplements the normal supply. And by way of that, Australia leads the world in this behind the meter type of supply. Alternative supply. Most of people would be across the concept of an alternative supply. In the past, this has generally been from a genset. But now we're starting to see battery systems being alternative supplies with automatic changeover devices. This example is one with a manual changeover switch and an inlet plug for a generator to connect to. There are two ways that an alternative supply can be connected to an installation, either hardwired or via an inlet plug. The inlet plug was mainly used for a genset, but there are also portable power stations, which is the black box in the bottom of the middle of the screen, which is an inverter and a battery in the box. This is very common with people who go camping and they need 230-volt power. We're also seeing EVs that can have the ability to power a 230-volt load, so they can be used as an alternative supply. In this example here, the charging plug has a 3-pin socket on the end of it that loads can connect to. Now, these devices can be plugged into the inlet plug as well and provide an alternative supply. Additionally, we're starting to see battery systems being used as an alternative supply with an automatic changeover device. Now, the main thing that I hope you take away from this part of the presentation is this. The problem with automatic changeover devices is there is no time limit on how quickly the alternative supply turns on. So what can happen is you could test an installation, isolate it, and then you test confirm that it's de-energized. You turn around, put your meters down, and then you grab a screwdriver to start doing some work. In that time that you've done that, the alternative supply could have kicked in and energized all or part of the installation. And so here's a real-world example that was taken from one of the Solar Victoria audits. What I want to discuss here is safe isolation and working safely. So how would you isolate this installation? Within this one single installation, there's 5 different supply types in this switchboard. There's the grid supply, there's the off-peak slab heating, there's the alternative supply from a generator with a changeover switch, there's also a supplementary supply coming from inverter 1, and then there's inverter 2, which also provides an alternative supply, which is all well and good when the escutcheon's in place and you could read the labels that are associated with the switches. Now, this is the same switchboard without the escutcheon in place. If you turn off the main switch, which red wire in this switchboard is not live? If you turn off the peak hot water, what has been de-energized? The generator main isolator, the generator changeover switch, the main switch for the inverter supply, or the main switch for the standalone system. There is way too much going on here. Even if you turn off all those main switches, there's a lot of live cables and a lot of live terminals within this switchboard. So the only way to work safely on this switchboard is to isolate all of the supplies, and you need to isolate them upstream. AS/NZS 4836, Safe Working on or near LV Equipment, has a requirement that all conductors in the area being worked on need to be de-energized or isolated. Not only that, to reinforce a point, the Electrical Safety Act also has a requirement. Section 43, subsection 4, is about circuits being energized from supply. Don't just turn off the main switches. Isolate all of the supplies at their source. So that means pulling service fuses, unplugging the generator, going to the supplementary supply inverter and turning it off its energy source, going to the battery inverter, shutting it down properly and turning off its energy source as well. Now, in terms of pulling the service fuse, a code of practice has been created to assist inspectors and electricians to remove the service fuse. This is available from the Victorian Service and Installation Rules website under Technical Information. The typical process and equipment required is listed here. It is taken directly out of the document. Alternatively, you can scan the QR code and it will take you straight to the document. If you have any follow-up questions, we can be contacted by any of these email addresses depending on what the question is. Thank you for your time.